In the previous video, we learned about how to draw Lewis dot structure for molecules. We look at how atoms within the molecule connect between each other, and in this chapter we are going to take a look at the shape of the molecule by using the theory called valence shell electron pair repulsion. Please read the OER textbook chapter section 6.2 for more detail of this. The homework that associated with this video is going to be the online Newton homework 6.2. There will be two parts. Okay, so this video will cover the valence shell electron pair repulsion theory, and the following video we will talk about the shape of the molecule and also polarity of the molecule as well. The valence shell electron pair repulsion, or VSEPR theory, is a model that is used to determine shape of the molecule based on the idea of the repulsion between electron domains within the molecule. So the electron domains around the central atom is what we are going to focus on. Okay, so pretty much we are going to make sure that the electron domains around the central atom will need to stay as far as possible from each other to minimize the repulsion for the electron domain. So let's give a definition of what is electron domain. So pretty much electron domains is the region of the occupied electron, right? So that's going to include single bonds, double bonds, triple bonds, lone pair electrons, and also an electron as well. So any region that there is the electron that is occupied, we consider that to be electron domain. Okay, and electron domain geometry is going to describe the shape of the electron region around the central atom. Okay, so pretty much we are going to look at the central atom. We're gonna determine the electron region around that central atom, and we are going to put them as far apart as possible. Okay, so that is going to be the shape or the geometry that we are going to look at. Okay, so in person class, there are always activities that involve with this. So for example, I would do the candies workshop here, where students will need to construct the shape of the molecule by looking at different electron domains and also try to put them as far as possible. So I'm going to supplement the video for this activity. So please watch the video for this activity, so that way you understand a little bit better why there are certain electron domain geometry. Okay, so if you watch the video of the activities, which is the supplementary video, we can conclude that there are going to be 5 electron domains start at the number of electron domain equal to 2. Okay, so 3, 4, 5, and 6. Okay, so that means in this case, the number of electron domain or the region around the central atom, if you have to, the representation of this would be if you have A as a central atom and X is the outer, what do you call, like the electron domain that is around the central atom is going to be 2, right? We count this as 1, we count this as 2. It doesn't matter whether you have single bond, double bond, or triple bond, all of these will still count as 2, right? Because these electrons that are sharing is considered to be one region, because you are counting between electron between the central atom and X, right? So this would be one region, there would be 2 region. If you change this to triple bond and one single bond, this is also still considered to be 2 region, because this is considered to be one region, even though it's triple bond, right? It still reside in the same region. Okay, so we count this as 1 and we count this as 1 as well. So total would be 2. So in this case, when you have the 2 electron domain, the shape of the molecule, since they need to stay as far as possible, therefore the shape of the molecule would be linear. Okay, so linear mean like a line, right? So the bond angle, or the angle between this bond right here, is going to be 180, because it needs to stay as far as possible from each other, right, to minimize the repulsion between this sharing electron, between these 2 regions of the sharing electron. Okay, so that's, therefore they have to be away from each other. Now, if you have 3 electron domain, which means if you have central atom, so this is the picture of it, right? So if you have central atom and you have two electron domain, they need to be the opposite side, so that way they are further apart. Okay, so when you have three electron domain, we are going to consider the central atom. Okay, so it's going to be around the central atom. Three electron domain means you are going to put three electron region right around the central atom. So if you put them as far as possible from each other, you are going to get this picture right here. And the geometry for this, or the shape of this electron domain, would be trigonal planar. Planar mean is in plane, is flat. Okay, trigonal mean like is like a triangle, right? It's a flat triangle. Therefore, in this case, the bond angle for this would be 120, right? So from here to here, that's 120, right? So this is 120. This is also 120 as well. This is also 120 degree. Okay, so those are the bond angle between the central atom and the two electron domains. Okay, so what would it look like? It look like this, right? So this is trigonal planar, where you have the central atom and you have three electron domain or three electron regions. Okay. Next one is when you have four electron domains. Okay, so which we are going to have four surrounding electron group around the central atom. So in this case, you are going to start with it look like a pyramid, right? So it look like a triangle pyramid, and then one is gonna go on top. So this is a three dimension, so it might look a little bit not very clear here. It look like these two are close to each other, but it's not. Okay, so this is represent three-dimensional picture. Okay, so don't so pretty much if you're looking at this one right here is actually coming toward us. This is going away from us, right? So this geometry is called tetrahedral. Okay, the reason why we don't do 4 as a and then with the x and x like this is because this is going to be flat structure, and the bond angle between each of these would be only 90 degree, right? However, when you have tetrahedral, the bond angle for these will actually going to be 109.5, which is larger than 90 degrees. So that means in this case, all of these are further apart than the flat one that I just showed earlier. Okay, so what does it look like in three-dimensional picture? So it's gonna look like this, right? So it's gonna look like a pyramid. Okay, tetrahedral. Tetra mean four. So tetrahedral mean like four faces. So it's have like one face right here, 2, 3 in the back, and then 4 on the bottom. So that's why it's called tetrahedral. It have like 4 faces of each of those. Okay. Okay, so again, this is the three-dimensional picture. All right, when we have 5 electron domains, then what we are going to draw is we are going to draw 3, which is like, it's going to look like trigonal planar on the bottom as a base. Okay, so of these, if you are looking at, this is, we are looking at side view, right? So that's why it's looking at this. If you are looking at bird eye view, like on top, from top to bottom, like if I'm looking at this, right? So if my eye is right here and I'm looking like that, what you are going to see is you are going to see pretty much the same as this one, right? So it's have trigonal planar base. But if you have only 3, it's going to be only trigonal planar. But we have 5 electron domain, therefore you need to include the other 2. The other 2 would go on top and on the bottom. Okay, so in this case, the electron domain geometry name for this is called trigonal. Okay, so it's similar to what we have earlier, right? So these two are kind of related, except this one is going to have one that is stick on top and on the bottom as well, right? So that's why if you're looking at this in 3 dimension, you are going to see that the top one look like a pyramid and the bottom one is also look like a pyramid as well. That's why we call bipyramidal, because we have 2 pyramid on the trigonal base or triangle base, right? So that's why we call trigonal bipyramidal. The bond angle for these, there will be two type. So one is you need to consider this type first. Okay, so because we have trigonal base, right, triangle base, and we have 2 pyramid on top and the bottom, This one on the vertical, okay, so this position right here we call axial position. Okay, so these two are called axial. And these three, which is the trigonal base right here, we call equatorial position. Okay, is on the triangle base. Okay, so the bond angle that we can determine is that if you're looking at this, right, it's easy, it's 90 degree, right? So that means in this case, 90 degree would be between axial, right? So axial and equatorial, so this would be 90 degree. Okay, now if you're looking at from different angle, for example, as I mentioned before, if I'm looking at this angle right here, you will see that from top to bottom, you are going to see a flat triangle, right? It's gonna look like that. So that means in this case, the bond angle between these going to be 120 degree, right? So between the equatorial position would be 120 degree. Therefore, in this case, for the trigonal bipyramidal, you have to specify the bond angle to two type. Okay, one is for the axial and the other one is for the equatorial. Okay, so equatorial would be 120. So again, equatorial would be from here to here, right? So that would be 120 degree, and then axial would be from here to here, right? That would be 90 degree. Okay. All right, so this is what it looked like, right? So that axial, right, would be 90 degree, and between equatorial would be 120 degree. Okay, so it's look like a two pyramid, right? So one on top, the other one is on the bottom, is on the triangle base. So that's why we call trigonal bipyramidal. Last one, if you have 6 electron domain, you are going to end up with the square base, okay? And you are going to have the top and the bottom as well, because you need to have 6 electron region total. So 1, 2, 3, 4, 5, 6, right? So if you add the surrounding atom, this is going to be called octahedral. Okay, so octa mean 8, hedral mean like the face of each of those, right? So in this case, the bond angle will equal to 90 degree. Okay, so how does it look like 90 degrees? So it look like this, right? So it's have one face, 2, 3, 4, right? 4, and then one on top and one on the bottom. So that's why we call octahedral. And each of these bond angle would be 90 degree. Now let's take a look at example. Example 1, we have these antimony pentafluoride. Okay, so we are going to learn how to count number of electron domain. Okay, so make sure that when you count number of electron domain to determine the electron geometry, you will need to consider only the central atom. Okay, so only specific central atom that we're gonna take a look at and predict the shape of the electron domain geometry. Okay, so in this case, we are going to focus on the antimony. Okay, so SB. So in this case, if you're looking at the group around antimony, you will see that the electron region that we have one region which is sharing between fluorine and antimony. Another region is with the another fluorine, right? And if you count off these, you are going to have total of 5 electron domain. Okay, so 5 electron domain, the geometry that we already see from the previous list, right? This is going to be called, so it looks like a triangle on the base, right? And then top and bottom, so it looks like a two pyramid. So this is what we call trigonal bipyramidal. Okay, so note that the wedge and dash that you see here, solid wedge and dash that you see here, is represent the 3 dimension of this molecule. Okay, so pretty much the line that you see is going to be on the same plane as the paper or as the board. Okay, the one that is represented by the solid wedge, that is going to be the one that is sticking toward you. The dash is sticking out away from you. So that's how chemists actually represent structure in 3 dimension. Okay, and the approximate bond angle for these, of course, because we have trigonal bipyramidal, therefore you need to specify 2 of them, right? So one is the axial position, so this would be 90 degree. Okay, the second one is between equatorial, so that would be from this to this, right? So it's the base, it would be 120 degree. Okay, so that means in this case you are going to have 90 degree for axial and 120 for equatorial position. Now let's take a look at example 2. I would like you to pause the video now and complete the number of electron domain and electron domain geometry, and also approximate bond angle for this molecule. Okay, so let's pause the video now to test your understanding, and then when you finish, resume the video again. All right, let's check your answer. So again, so we are looking at the electron domain geometry, and we are going to consider the central atom in this case. Okay, so which means it's going to be around carbon. Okay, so when we see around carbon, so how many electron domain around carbon then? Okay, so one region is count between carbon and chlorine that is sharing, so that would be one region. Second region is carbon and another chlorine. Okay, so they want to stay as further as possible from each other. The next one is going to be between carbon and oxygen. Note that even though oxygen and carbon bond double bond, but still this is going to be reside in the same region. So that's why total number of electron domain or electron regions for this molecule around carbon would be just 3. So that means single bond count as 1, double bond also count as 1 as well, and then triple bond count as 1. Okay, so total, add them all up together, you're going to get 3 in this case. Okay, now the electron domain geometry. Okay, so because we have electron domain 3, the electron domain geometry would be what? So if these 3 regions need to stay as far as possible from each other, it's going to give you the shape of trigonal planar, right? So it's going to be in plane. Okay, the approximate bond angle of this would be between each of these, right? So between this one, right? So this one would be 120 degrees. Okay, so that would be the bond angle for trigonal planar. So this is an example of how to predict electron domain geometry. First, you will need to draw correct Lewis structure first. So as you see, right, without knowing the Lewis structure, you will not know how many electron domains. Okay, by knowing the number of electron domains, then you will be able to find or to predict the geometry of it, and then you will be able to find out the bond angle. Next, we are going to take a look at the effect of lone pair. So I have 3 molecules that we are going to compare them. These 3 molecules are methane, ammonia, and water. And if you're looking at the first one, methane doesn't have any lone pair, ammonia has 1 lone pair, and water has 2 lone pairs. Okay, so this is according to the Lewis structure. And how is that going to affect the geometry of the molecule? That's what we're going to take a look at. Okay, so the number of electron domain for each one of these are equal, which are equal to 4. The reason for that is because we count all the electron region as 1, right? So we count single bond, this is 1 electron region because the electron occupied between carbon and hydrogen, we count that as 1. So 1, 2, 3, 4. Same thing for ammonia as well, right? So the electron are sharing between nitrogen and hydrogen. That's 1 region, 2 region, 3 region. And also we have the region of the lone pair. The lone pair also needs space, right? It's occupy space. So we need to count them as well as 1 region of the electron that is occupied. For water, we have 2 regions from the sharing electron between oxygen and hydrogen, and because we have 2 lone pairs, each lone pair will occupy 1 electron region, right? So these are 2 separate regions, so total would be equal to 4. Therefore, in this case, if you are also counting so how is this coming from, right? So as I mentioned earlier, so it's coming from the bonding and the lone pair add together, right? So pretty much if you have the bonding domain, right, so that's gonna count, you have to count it all, and because there is no lone pair is equal to 0. For this one, the number of electron domain coming from 3 bonding domain, right, and then 1 lone pair. And for oxygen, for water, you will have 2 bonding domain and 2 lone pair domains. Okay, now the electron domain geometry based on what we already see, right? So because of this, they have 4 electron domains. Therefore the electron domain geometry for this one is what we call tetrahedral. All of them are tetrahedral. Okay, now the approximate bond angle, if you see the actual value that is reported here, I don't want you to memorize this, but what I want you to know is that the relative, right, the relative value, what happened, this is the ideal value that you will need to know. But when you introduce lone pair, you don't need to know the actual bond angle for those, but you need to know the relative value of it, and you need to understand what it means, right? So as the number of lone pair introduced to the electron domain region, you will notice that the bond angle start to decrease, right? It gets smaller and smaller. In this case, you will see that the ideal bond angle for tetrahedral is 109.5, and as the number of lone pair get introduced, the bond angle will get smaller and even smaller when you have two lone pair, right? So this is a lot less than 109.5. So what is it then? So according to the data above here, right, according to this, we can conclude that bond angle decreases as the number of lone pair increases, right? So if you introduce, whenever that you introduce lone pair into the molecule, you are going to observe decreasing of the bond angle. The bond angle between between two bonds will get closer to each other because lone pair is going to push that closer. Okay, so the reason for this is because the repulsion effect or the strength or the magnitude of the repulsion are not the same. The repulsion for the one that have least repulsion to the strongest repulsion is that when you have lone pair, right? So when you have two lone pair, the lone pair has the strongest repulsion. They repel each other a lot because there is no nuclei to share between these lone pair electron. Is only shared with only oxygen nucleus, okay? And the second strongest would be between bond pair and lone pair. So it's between bond pair and lone pair, right? So bond pair and lone pair here. The reason for that, again, because this is purely electron, right? This is sharing electron between two nuclei. So therefore, in this case, the repulsion for this would be stronger, but is weaker than lone pair, okay? And the last one, the least repulsion would be bond pair, which means if you have these two, right, they are going to repel each other at a certain amount, but is actually going to be weaker than when you have lone pair and lone pair. So therefore, in this case, you are going to get the ideal bond angle for the bond pair for this. Okay. So again, the reason why lone pair require the reason why lone pair has more repulsion effect is because the lone pair electron require more volume or more space. If you think about this, right, as I mentioned before, when we talk about bonding electron pair, right, which is the electron between each of these bond, right? So that's what we call bond pair right there. They are require less space because the electron density is sharing between two nuclei, right, between the central atom and the outer atom, right, between central atom and the outer atom. So it's going to require less space than the lone pair electron, right? Because lone pair electron is on only the central atom. So it's going to, there is nothing to like, minimize that electron density. So therefore it's going to require more space. In this case, it's going to require more space. So it's pushing off this bond pair even closer to each other. So therefore the bond angle would decrease as the number of lone pair increases. Okay. All right, so the next thing we are going to take a look at is the shape of the molecule. Okay, so what we are considering right now is the shape of the molecule that include all the electrons that around central atom. Okay, but when we talk about molecular geometry would describe the three-dimensional shape of just the atom. Okay, so we're looking at the shape without looking at the lone pairs. Okay, electron domain geometry, we're looking at the shape of all electron regions included. Okay, all electron domain included. But molecular geometry, we are looking at the shape of the molecule by excluding the lone pair. Okay, so what do I mean by that? Okay, so pretty much in this case, this is the picture that represents electron domain geometry. This is the picture that represents molecular geometry, what the molecule look like exactly, right? So when you exclude those lone pair, what does it look like exactly, right? So pretty much this, there will be a name for this. If the electron domain geometry it doesn't have any lone pair at all, you probably end up to have the same, you will end up having the same shape for molecular geometry. For example, in this case, methane would be tetrahedral, right? Because there's no lone pair effect. Okay. However, when we introduce lone pair, the name of molecular geometry will not be the same as electron domain geometry anymore. Okay, so if you're looking at this picture right here, it's not going to be the same as tetrahedral, right? It doesn't look like tetrahedral. These have its name. Okay, so it's look like a pyramid and it's look like it's have a triangle base, right? Or like a three faces of for this. So this is called trigonal pyramidal. Okay, trigonal means three, right? Triangle, and then pyramid, it look like a pyramid, right? And for water, of course, if you're looking at the molecular geometry by excluding the lone pair, you will see that these doesn't look anything like tetrahedral, so therefore it have its name. Okay, so this one is called bent. Okay, so we are going to pretty much derive the molecular geometry from the ideal electron domain geometry without the lone pair. When you start adding lone pair, and that's how all of this name is going to be derived from. Okay, so bond angle for these, as I mentioned earlier, right? So as you see that as the number of lone pair increase, you are going to see that the bond angle will decrease. Okay, the more lone pair you introduce, the what do you call it, the smaller bond angle. Okay, so pretty much this is what I mentioned earlier. So pretty much these two are deriving from tetrahedral, right? So as you introduce one, right, you're removing one and replaced by the lone pair. This is going to be trigonal pyramidal. And when you remove one more, right, by replacing it by lone pair, you are going to end up with bent. Now let's take a look at how we can derive the molecular geometry from the electron domain geometry. So as I mentioned before, so pretty much we are going to start with the number of electron domains. Okay, so if you know that and you know the number of lone pair, it will also help you to determine molecular geometry as well. Okay, so if you have two electron domains, which means you have these two regions and you have zero lone pair, the electron domain geometry would be linear. The molecular geometry also going to be linear as well. And also if you introduce one of these to be a lone pair, for example, AX, and have this another one here, right, as the lone pair, this is still going to be linear. Because if you think about it, right, so if you think about this, the shape between X and A is still going to be linear, right? It's the line right there. So therefore, in this case, if you introduce lone pair in the linear electron domain geometry, it will not do anything, right? So it's going to be, the molecular geometry will still be the same. Okay. So now if you have three electron domains, we learned previously that this is called trigonal planar. Okay. For trigonal planar, when there is no lone pair, the molecular geometry and the electron domain geometry will be the same, because you have not because molecular geometry is only excluding the lone pair, right? If you don't have any lone pair, then it's going to be the same as electron domain geometry. So for this one, when there is no lone pair in trigonal planar, molecular geometry will still going to be the same, which is trigonal planar. Now, when you introduce one lone pair, okay, so when you introduce one lone pair, so let's say like I'm removing this X right here and replacing by lone pair. As we look at earlier, the lone pair occupy more space. Therefore, this lone pair right here is going to push these two bonding pair to be closer to each other, right? Because this bonding pair is going to be away from this electron lone pair, because it has higher repulsion, stronger repulsion in this case. So therefore, the bond angle would be less than 120 degrees. How much? You don't have to know, right? Just know that it's going to be less than 120 degrees. Okay, so if you're looking at these, because the molecular geometry is when we are excluding or when we omit the lone pair, therefore in this case, if you think about the shape between X, AX like this shape is look like bent, right? Because bent, so the name of this was called bent. Okay. And now if you introduce one more, let's say if you introduce one more lone pair, right? So you have two lone pair now. And another one, I'm going to replace this X with that lone pair. This one, if you're looking at it, right, molecular geometry for this would be what? Just a linear, right? Because it's just going to be a line between X and A, right? So this one would be linear. So that means if you want to include more lone pair, you are welcome to, right? But eventually, it's going to get down to the linear, right? The more you add finally, right? So if you have only these two atom left, right, it's just going to be linear. All right, next one is when we have 4 electron domains. Okay, 4 electron domains, we call this tetrahedral. Again, how we draw this would be a pyramid, right? And then you have like one on top, a triangle pyramid, and then one on top. So the ideal bond angle would be 109.5 if there is no lone pair. The molecular geometry and the electron domain geometry will still going to be the same. Okay, but once you introduce lone pair, okay, so I'm going to introduce lone pair on the top one, right, like here. Okay, the bond angle would get pushed closer together because it's got pushed by the lone pair, because lone pair occupy more space in this case. Therefore, in this case, the bond angle would be less than 109.5. And we already see this structure. This structure, it looks like a pyramid, right? It's called trigonal pyramidal. Okay, now if you introduce 2 lone pair, okay, so you introduce 2 lone pair, I'm going to add lone pair right here. It's still going to be bent, right? It's look like, it's look like bent. So the bond angle would get smaller. It would be 109.5. Now if you introduce one more, as I mentioned earlier, right? So if you introduce one more, what you're going to end up having is you are going to end up with linear again, right? Because it's just A and X, so that would be linear. Okay, so that means the more you add until you have only two atoms left, it's just going to be linear. Okay. All right, so the number 5, when we have 5 electron domains, okay, so electron domain geometry for this is trigonal bipyramidal. Okay, the molecular geometry when there is no lone pair is going to be the same, which is trigonal bipyramidal. Okay, so these two are going to be the same when there is no lone pair. Okay, now when we introduce one lone pair, this is what I want you to focus on right here. Is it going to be the same whether we replace by this X, or this X, right? Because when we saw this earlier, if you go back to this, right, it's pretty much you can replace at any one of these, but it just depends on how well you actually understand the 3 dimension. Okay, so the easiest one is to add to the top first, so that way it's easier for you to like look at and see that it look like trigonal pyramidal. Okay, so that's why I introduced to that part. You can also introduce to this X as well. It's still gonna be trigonal pyramidal. Same for this X as well. However, it's not the same for trigonal bipyramidal because the axial and equatorial position make them to be different. The location of these X, if you place the lone pair on, there is going to be one specific location that is going to be more preferable. Okay, so lone pair must be added to the equatorial position, and here is why. Okay, so if you think about this, if you add lone pair to the axial, lone pair is going to be only 90 degrees away from all these bonding pair. However, if you put the lone pair on equatorial, it's going to be away from this lone pair, and the rest would be 120 degree, right, between the lone pair and the remaining atom, right, the bonding electron region here. So therefore, in this case, what you need to do is you are going to replace the easiest way for you to look at and see what it look like. You are going to replace with this X. It doesn't matter actually, but it's as long as it's going to be X on equatorial, you are going to end up with the same picture. Okay, so the easiest way, because we are looking at 2 dimension right now, okay, so the easiest way for you is replacing this X by the lone pair. And this is still going to be, it's going to be a little bit less than 90 degree because the lone pair pushing it, right? And also same thing for the 2X on the equatorial as well would be less than 120 degree. And again, the reason why we place it right here, because at this point, right, is further apart than if you place the lone pair right here. It's only 90 degree apart. Okay. So these right here, if you rotate it, pretty much if you flip this, right, if you rotate this, okay, this structure right here is called seesaw. Okay, so that means in this case, when you introduce one lone pair to trigonal bipyramidal, you are going to end up with seesaw geometry or the shape of the molecule that look like seesaw. Okay. The second one, or the second lone pair that you will need to add, the easiest one would be, you can add 1 and 2 right here, or 1 and 2 right here, or 1 and 2 right here, right? As long as they are on equatorial, that would be the correct answer. But I'm just gonna try to make it clearer for you to see. Okay, so the easiest way for you to see in two dimension is to add the lone pair in these two. Okay, because when you add lone pair in these two, is put these two electrons on equatorial further away from each other, which is 100 degree, right? And also is further away from this bonding pair as well. So in this case, what you are going to have, if you rotate this, okay, so if you rotate this, if you flip this like this, it look like T-shape. So the shape of the molecule for this one is called T-shape. Okay. Next one, the third one, if you introduce one more, again, still have to be on the equatorial. So on all of this base right here needs to be replaced by lone pair, right? You have 3 lone pair. So now this is just the linear, right? If you rotate it. Okay, so this is just the linear. Okay, so that means in this case, the seesaw, T-shape, and linear are derived from the trigonal bipyramidal, which is going to be the lone pair that is present as part of the electron domain group. All right, for 6 electron domain, which is octahedral, when we have 0 lone pair, the molecular geometry will still be octahedral. When we introduce 1, okay, so if I introduce 1, what we're having is going to be square planar, right? Because it's, not square planar, square pyramidal, because it's a pyramid that have a square base. Okay. The second one, if you introduce the second one, does it matter whether I introduce X here, here, or here? In this case for octahedral, it doesn't matter because all of these bond angle are 90 degree, right? So between here and here is also 90 degree. Between here and here is also 90 degree. So it doesn't matter in this case. Okay, as long, because you want to put lone pair away from each other. Therefore, in this case, I'm going to have to put lone pair on the opposite side, because if I put here and here is too close to each other, right? It's only 90 degree, but here to here is 180 degree, right? So it's better. So this structure right here, this shape is called square planar because it's flat, right? It's in plane. Okay, this is square pyramidal because a pyramid. Okay, so this is square planar because on the plane. If you introduce one more, right? So if you already introduced 2, the third one, I'm going to replace this one, right? The third one, I'm going to replace this X with the lone pair. This one right here, if you tilt it, right? Or if you rotate it, it's going to be T-shape. Okay, so again, so this is going to be T-shape. And if you introduce one more, you have to introduce on the opposite side of this, right? So that way it's a further away. So this one would be linear again. Okay, so that means in this case, all of these molecular geometry derive from the octahedral when you introducing lone pair to the Lewis structure. Okay, so what do I mean by that? Okay, so let's take a look at example. Okay, so in this case, what you're going to see on the exam is you are going to need to be able to draw Lewis structure and use Lewis structure to help us determine the electron domain geometry and also molecular geometry as well, and including the bond angles between the bonding pair. Okay, so xenon dibromide. Okay, what should be the chemical formula of this? Xenon is X. So, sorry, can you also correct these two instead of 3D structure? Can you correct that to 2D geometry? Okay, so xenon dibromide. Okay, so it's going to be XeBr2, right? Diamine 2 bromide. Okay, so this is molecular compound because contain 2 nonmetal. Okay. In order to draw Lewis structure, we need to count the total number of valence electron. 8 from xenon, right, to bromine. Each bromine is 7 electron, so total would be 22. As we looking at in the previous video, right, to draw this, you are going to start with the single bond first, okay, then count the number of bonding, right? So in this case, the single bond contain 2 sharing, total would be 4. So there are 4 electron bonding. So what we have left would be 18. We have 18 left. And when you have 18 electron left, you are going to distribute to the outer atom first so that the outer atom have an octet, which means you need to distribute to these two bromine. Okay, so that way the two bromine has an octet. This bromine contain only 2 electrons, so it needs 6 more. So we're gonna add 6 more to those. We still have what? How many we have left? So we already 6, right? 12. So 12, we would have 6 more to go, right? We already spent 12, you have 6 more to go. So 6 more is going to go into the central atom. Okay, so again, this is one of the exception of the octet rules, because xenon is on the 3rd row and beyond. Okay, so it can accommodate more of the electron. Okay, so in this case, if you're looking at this, okay, so this is Lewis structure. Lewis structure is not necessarily going to be the same as the correct geometry. You can draw Lewis structure in any way you want to. Okay, so for example, I might draw Lewis structure as BR, XE, BR like this, and like this, right? So this is still correct, right? As long as you have the correct number of electron around each of those, right? To make sure they have an octet, and you spend off this total number of electron as we calculate, right? As long as you draw to have the correct connection and correct number of electron, this is correct Lewis structure. But the correct Lewis structure might not be the same as the geometry. So that's what we will need to determine, right? Whether how you draw it like this is already correct shape, we don't know. We need to determine the electron domain geometry. Okay, so what we can do is that according to this, we are going to look at electron domain, which is going to be around the central atom. So in this case, we have 5 regions, right? So we have 1, 2, 3, 4, and 5. Therefore, electron domain would be 5. Okay, bonding groups. How many bonding groups around xenon? Okay, so the answer would be, oh, sorry. Let me actually so because electron domain equal to 5, electron domain geometry would be trigonal bipyramidal. Okay, so what would be the trigonal bipyramidal? Well, we already see earlier, right? So xenon, okay, trigonal bipyramidal look like this, right? It look like triangle base on the bottom, and then we have top and bottom like that, right? So trigonal is bipyramid, right? So pretty much we have 2 bromine. So 2 bromine. And then because we have 3 lone pair here, okay, so those have to be on the equatorial, right? So I'm going to add those 3 lone pair. So these would represent the correct geometry for bromine. Oh, sorry, for xenon dibromide, right? Because you are going to draw it as the electron domain geometry in this case. So this is the correct structure for that. Now for the molecular geometry, what you are going to consider is you are going to consider the number of bonding group and the lone pairs. Okay, so the bonding group that we have would be 2, right? Because these 2 are the bonding group is sharing between bonds. This is bond, this is not bonds, right? It's just the region of the electron. So we have 2 bonding group and 3 lone pair. Note that you can draw the structure like this, right? Or if you tilt it or rotate it, it also can be shown like this too. Whichever one that you are most familiar with and feel comfortable with, stick with that one. I just show you another way to represent this. Okay, so again, this structure right here is trigonal bipyramidal, which is identical to this structure right here. It is also trigonal bipyramidal as well. It's just different view. Okay, so if I rotate this one, it's going to be this, right? Now, because we already see it contains 2 bonding group and we have 3 lone pairs, therefore in this case, when we consider the molecular geometry, we are going to ignore the lone pair, right? So let's pretend that we ignore this. If you ignore all of this, you consider only just the bromine, right? So you consider just bromine and the central atom. So this one right here would look like a linear, right? So that means in this case, molecular geometry would be linear. The bond angle is going to be the angle between bonds. Okay, so bond angles, angle between bonds. What are the bonds is between this, right? That's 2 bonds. So it's going to be angle between that. So that would be 180 degrees. All right, so the last part of this example is talk about polarity. I would like you to skip this part first. We are going to revisit this later when we talk about how to determine polarity of the bond and also the molecular polarity of the whole molecule as well. Okay, so let's skip this for now. All right, so the next thing we're going to take a look at is we're going to take a look at the shape of the large molecule. So we're going to look at organic compound that look like this. What is organic compound? Well, organic compound is the molecule containing carbon and hydrogen, right? So especially carbon. So in this case, this is huge, right? So how can we determine the shape of the molecule? According to the Vesper theory, right? So based on the electron pair repulsion theory, we are going to look at the central atom one at a time. Okay, so for example, in this case, the reason why we have several central atoms because we're going to look at them one at a time. Okay, so n equal to 1. Okay, so n equal to 1. We are going to determine both electron domain geometry, okay, and also molecular geometry as well. Remember, this one include everything, right? Include everything. This one is when you exclude the picture of the lone pair. Right, so if the molecule has lone pair, you need to make sure that you exclude that, right? You kind of like cover it and see what it look like exactly. So these two maybe or maybe not, like they might be the same or they might not be the same. It's depend on whether the molecule has lone pair or not. Okay, so or whether the central atom has lone pair or not, because we are focusing on specific central atom. Okay, so let's take a look at n equal to 1. Okay, so when we look at n equal to 1, okay, so this is the label nitrogen 1 is the labeling with number 1 right here. What is the electron domain around this nitrogen? Right, so pretty much we see that there is one lone pair. So one bond, another bond, another bond. So this would have 4 electron domains. Okay, so how many lone pair? Well, clearly it's just one, right? So one lone pair. So we're not going to look at lone pair yet. In order to determine electron domain geometry, you are going to determine from the electron domains, okay, which is include lone pair and also single bond as well. Okay, so this is tetrahedral. Okay, what does tetrahedral look like? Okay, so a tetrahedral would look like this, right? So it would look like that, right? So nitrogen would be in the middle. Okay. Now, if you're looking at number of lone pair, there is only one. So therefore, in this case, because it look like tetrahedral, okay, so I'm going to draw that, and with one lone pair, okay. So if you kind of like ignore this part right here, right, if you kind of like ignore this part, you're going to see that if we consider only the bonding, right, which is the molecular geometry bonding pair, it's going to look like a pyramid, right? So that's why this one is called trigonal pyramidal. Okay, now C equal to 2. Okay, so C equal to 2. The number of electron domains, okay, double bond count as 1 because it requires only one region, right, one space between carbon and oxygen that sharing those 4 electrons between each other. 2 region, 3 region, there's no lone pair. So in this case, we have 3 electron domain. Therefore, electron domain geometry would be trigonal planar. And because there is no lone pair, therefore, in this case, molecular geometry and electron domain geometry would be the same. Okay, so I would like you to go ahead, okay, start working on, pause the video, okay, so start working on N3, C4, C5, C6, N7, and oxygen. Okay, so complete these to test your understanding and then resume the video again when you finish. All right, let's take a look at your answer for N3. N3, the number of electron domain equal to 3. So this is trigonal planar. Okay, lone pair, since we have 1. So the molecular geometry would be bent. Okay, C4 would be trigonal planar for electron domain geometry and also the same as molecular geometry as well because there is no lone pair and there are 3 electron domains. Okay, C5, same as C4. Okay, so same as C4, only 3 electron domain, no lone pair, therefore electron domain geometry and molecular geometry would be the same, which is trigonal planar. C6 would be the same as C4 and C5 in this case, right? C7, okay, C7 has 1, 2, 3, 4 electron domains, so it would be tetrahedral, but there is one lone pair, therefore the molecular geometry would be trigonal pyramidal. Okay, now what about oxygen? Okay, so if you're looking at oxygen, okay, so oxygen contain 1 electron domain, 2 electron domain, 3 electron domain. Okay, so oxygen contains 3 electron domains. Oops, sorry. Oxygen contains 3 electron domains. Oops. Okay. And we see that lone pair around oxygen, there are 2 of them, right? So we have 2 lone pair, 1, 2. So if you ignore oxygen, oops, sorry, 3 and 2. If you ignore the lone pair in oxygen, so if you ignore this part right here, you are going to see that what you are going to see is going to be only the region between carbon and oxygen, right? So this look like a linear, right? So that means in this case, because we have 3 electron domains, the electron domain geometry would be trigonal, planar. But because we introduced 2 lone pair, therefore in this case, it's going to look like a linear for the shape of the molecule, right? Because when you ignore the 2 lone pair, it's going to look like linear. So therefore in this case, this one would be linear. Okay, so next example, I would like you to pause the video and complete the electron domain geometry and molecular geometry based on this Lewis structure that you see here. If the electron domain geometry and molecular geometry is not the same as the Lewis structure, I would like you to draw the 2-dimension structure that is the correct representation of those geometry. Okay, so by the way, we are going to revisit this molecular polarity in the next video. Okay, so we're gonna revisit this later. So let's pause the video now and complete the rest of this. Okay. All right, let's take a look at the first one. Okay, so the first one we have SF2Cl4. Okay, so SF2Cl4. This one is called trans because the 2 fluorine are on the opposite side. Okay, this one is also have the same chemical as well, but this one is called cis because the 2 fluorine are closer to each other. So pretty much these two, even though they have the same chemical formula, but because geometry are different, so you're gonna see later that the property will be different as well. Okay, so when we talk about the polarity. Okay, so but for now we are going to focus on only the electron domain geometry and molecular geometry. So these two, right, contain 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So these two contain 6 electron domains. Therefore, the electron domain geometry would be octahedral. Okay, and because if you're looking at sulfur, there's no lone pair around sulfur either. So therefore, in this case, both of the electron domain and molecular geometry would be octahedral. Okay, so both of these would be octahedral. Now, what about silicon tetrachloride? Okay, so in this case, we see that we are, again, when we're looking at electron domain geometry, right, when we're looking at the geometry, we're looking at the central atom. Okay, so we're looking at this as central atom. So for silicon tetrachloride here, when you count the electron domain around silicon, there are 4 of them. So therefore, electron domain would be, what is it? Is it going to be square planar or tetrahedral? The answer is it's going to be tetrahedral. Okay, so this structure of Lewis structure, again, Lewis structure, you can draw anywhere you want to, right? It's not the correct shape. It doesn't have to be correct shape. But molecular geometry is the actual geometry of the molecule, the shape of the molecule. You need to represent these to actually matching with the correct geometry. So this is not how it looks like in reality. In reality, this molecule going to look like tetrahedral. What would it look like, right? So it's going to look like this, right? So it's what do you call it? It's gonna start with the pyramid base, right, and one on top. So you're gonna end up with tetrahedral geometry that look like this. Okay, so it's not flat like that. Okay, so this is gonna be the correct geometry, and because there's no lone pair around silicon, therefore both electron domain and molecular geometry would be the same, which is tetrahedral. Next. Okay, so dihydrogen sulfide. Okay, so this is not the acid because if it's an acid, that would be AQ with it. Okay, so in this case, what should be the electron domain geometry then? Well, again, you are going to count around the central atom. We have 1, 2, 3, 4, right? So in this case, we have 4. It's going to be tetrahedral again. Okay, what about, is this already in tetrahedral? No, the answer is no, right? It looks like a linear and it looks like, yeah, it's just the Lewis structure. It's not the correct geometry. So we need to put this into correct geometry, which is tetrahedral. So how do you draw tetrahedral? It's going to be like this, right? You start with the pyramid base and then one on top, right? So you're going to start adding the hydrogen and also lone pairs. Okay, tetrahedral for electron domain geometry. Is it going to be the same as molecular geometry? The answer is no, because you introduce two lone pair in here. So that means when you are introducing lone pair, the molecular geometry and electron domain geometry would not be the same. So in this case, for molecular geometry, you kind of like need to kind of like ignore that lone pair, right? And looking at only the central atom and the bond, right? So if you're looking at this one look like what? Bent, right? So therefore, this structure would be bent, right, when you ignore the lone pairs. Okay, so pretty much this is what we see so far, right? So the major electron domain geometry are listed here, and when you're looking at molecular geometry, you are going to replace each of these by lone pair and looking at what would be the new shape of the molecule, right, by looking at this. For example, if you introduce lone pair to this one, right, you kind of like get rid of that, so it would be linear. If you introduce one lone pair here from trigonal planar, it would be bent. If you introduce one more, it would be linear, right? For tetrahedral, right, so if you then have lone pair, would be tetrahedral. When you introduce one lone pair, right, that's look like a pyramid. If you introduce another lone pair, that's look like bent structure, right? If you introduce one more, that would be linear. Okay, same thing for trigonal planar as well, except you will need to make sure that you introduce it on the equatorial position, right? So if you introduce one here, right, it look like seesaw. Okay, if you introduce one here, that would be T-shape. If you introduce one here, that would be linear, right? So if you introduce one more, it's still going to be linear too. Okay, now for octahedral, it doesn't matter which one you introduce because they are having the same bond angles. Okay, there is no axial or equatorial in this case, right? So because they all have the same bond angle of 90 degrees. So when you introduce lone pair, right? So if you introduce here, this would be square pyramidal. It looks like a pyramid, but it's a square. If you introduce one right here, the rest of it would look like square planar. If you introduce one more, that would be T-shape. If you introduce one more, the opposite, that would be linear, right? So that's how you derive the molecular geometry, by knowing the electron domain geometry. And when you have the lone pair, you continue adding those to get the correct molecular geometry. Okay, so pretty much after this video, now you should be able to start working on online homework chapter 6.2.